phi n1 is our first order correction in the wave function. So this is actually obtained by sigma m not equal to n phi m h prime phi n en0 minus em0. Now this is expression for our first order correction in the wave function. So this is something that we have to investigate. We know what is the h prime here, and the states are unperturbed states are something that we know. Okay, we know the harmonic oscillator, what these quantities are, and you know what unperturbed energy changes you can calculate by using the energy expression of harmonic oscillator at different depending upon the values of m and n. And obviously as long as m is not equal to n, this quantity is not going to be equal to 0. Okay, so we have to, first thing is that it's not the exactly same component that we have done before. In the previous case, when we have done the correction of energy, we have both phi n, and we have some easy way of doing that. But in this case, we have to find out what and all are the terms which are going to contribute, first of all, to the summation. So let's say there are let's take the number of states are something like 10 or 15 or whatever. 10, let's take 10 different states are there, and the h prime here is an operator which is doing the correction not on all those states, some of the states. So when suppose it is acting on the initial first 4 states, this h prime is changing the some way it is changing the states from 1 to 4. Okay, so those are the terms which are going to be slightly getting modified, and those are the terms which are going to have any correction factor at all. Remaining terms which is not having any influence on the perturbation will not be changing. That will not be contributing this sigma value. That's kind of obvious for us. So the terms which are going to contribute, how do you understand that? In that case, you know this this is actually the unperturbed states of the harmonic oscillator. So when the h prime is acting on the state, let's say phi n h prime is acting, and any value apart from phi m if you are getting here, that value is going to be 0, right? After the application of this operator, if you are getting something like phi m plus 1, since the orthonormality of this basis, we know that quantity is going to be 0. So what kind of components that we have to identify is that after the application of this perturbation, the state phi n has to change into phi m. So that kind of states we have to identify. So if there is no change, n is equal to m, that case is not need to be taken care, because our summation, our condition is that m is not going to be equal to n. So okay, let's begin by putting some values here. H prime, we know h prime is nothing but hp, which is c x cap raised to 4. X cap is nothing but h cross by 2m omega, or in terms of k we have rewritten it. Okay, a plus a dagger whole raised to 4, and this whole to the power 2 it will come, and that's all it is. Is actually x prime raised to 4. Okay, so my phi n1, phi n1, this is how I call it, first order correction. So I'm not putting the phi factor here. Okay, just putting sigma should not be skipped, not equal to n. m is there, h prime, that constant is coming out. Okay, I'll write it later. M, and what else is there? A plus a dagger whole to the power 4 n divided by e n0 minus e m0, and the constant term which are there, which are c, this is like cx raised to 4, so c will be there, and this constant which are there, h cross raised to cross by 2 mk. If I am putting k, it will become k square, and 1 omega factor will be coming on top. So this is the term which is there, ch cross omega by 2k square whole square. So we have to identify what and all are the components which are going to contribute by this kind of an operator. To identify that, we have to understand what sort of change for the state and this operator is causing. So to understand that, let me put this equation here and just expand this expression of a plus a dagger whole power 4. So this is, as before, we will write something which is knowing, that is a plus a dagger whole square into the same term, right? A plus a dagger whole square. Okay, this is something that I know, a square plus a dagger square plus 1 plus 2 a dagger a, that we have found out earlier, and that operator acting with the same a square plus a dagger square plus 1 plus 2 a dagger a. Okay, now to identify each of these operations individually, I'll multiply them. So first term multiplied with another one, it will become a raised to 4 plus first term with the second term, it will produce a square a dagger square plus first term with the third. These two terms I will take together because it's both of them, one is not changing the state, and 2 a dagger a will not be changing the state. So this is actually the terms which are not changing the state, so I'll just multiply it together. So a square 1 plus 2 a dagger a. Okay, so a square multiplication is over. Now a dagger square is multiplied with a square, a dagger square multiplied with a dagger square, which will give you a dagger raised to 4 plus a dagger square multiplying with the constant a dagger square with 1 plus 2 a dagger a plus next component is this 1 plus 2 a dagger a multiplied with each of these terms, right? 1 plus 2 a dagger a multiplied with the a square plus 1 plus 2 a dagger a multiplied with the a dagger square plus 1 plus 2 a dagger a whole square. So these are the kind of terms which are involving on the expansions. So now you can put this inside our summation, and you can just identify which are the states. Okay, right now I'm not going to bother about this coefficients which are there. I just want to identify which are the m states which are going to really contribute for this summation. So I know this h prime is having this quantity. I'll just skip this constant right now. I will put it later. A plus a dagger whole raised to 4 is there. So that expansion I know, whatever I got that quantity, when I put that quantity over here, all those components will be changing this phi n in a different manner. That phi n and this phi m, whenever it is equal to, whenever they are same, that will contribute, otherwise it will not contribute. So whatever which are coming here, the terms which are not changing the states are not really important for us, so I will straight away remove them, because m is not equal to 0. So the perturbation ultimately has to change the state, otherwise it will not contribute. So those states which are, those components which are not changing the state at all is one is this quantity 1 plus 2 a dagger a dagger and a both are there. So this is not going to contribute, it's not changing the state. Anything else? Obviously this will change the state by 4. This is not going to contribute, right? It will not change the state. No need to bother about that. This will change, this will not change, this will change, this will change, and this will change, and finally this also will change. So remaining terms will be changed in the state. So all those components, what are the states which are produced by each of those component, will be there in our summation. So these terms I am removing directly. I don't want, I know that they will not contribute anything. Okay, now let me put the number here. Now just identifying the terms which are coming. So one is m. First, okay, let me do it. I'll just apply the operator a raised to 4 on a state n, and it will produce some number. Right now I just want to find out the state, so I'm not putting the coefficients. So 4 times a operator is acting on n, you know, it will produce n minus 1, n minus 2, n minus 3, n minus 4. It will bring the state into n minus 4. Okay, so that is first state, and here a square is changing the state. This quantity is not changing the state at all, a dagger a, so a square is changing, so that will change the state n to n minus 2. Third one will not be contributing. A dagger will increase the change due to a dagger will change the state n into some number n plus 4. Sorry, 4. Okay, now next term which is coming is this quantity. What is the change this is causing? This will not change anything, this will increase the state by 2, right? So a dagger square will change the state by 2, n plus 2. Now okay, what about this quantity? That is nothing but here there is a constant multiplied with the a square, so it's reducing the state by 2. So that will be the same state which is produced by this quantity. So there is no other change. So say, the state is already there in our calculation, so no need to write it second time. So that state is already written. Now another one is this quantity, again a dagger square. So that also we have considered. So these are the four possible states of M that will contribute to the summation. So right now I know what are the possible values of M. To identify that only I have done this all. So possible states of M, let me write. M is 1, n minus 4, n minus 2, n plus 2, and n plus 4. These are the four possible states of M. Okay. Oh, well, one thing I missed here is in this expression, it's just a number right now. We will be having the direction component also, right? So that will be like, so this is going to be in the direction of phi m. We are putting the correction of phi m. That will be there. Otherwise, these are just numbers and they will add on. So first, we will be putting the correction of phi m when m is equal to n minus 4. Then we will put the correction of m minus 2, n minus 2, n plus 2, and n plus 4. 4 of the states. Okay. As we identified the terms, now we have to identify the coefficients also. So to identify that, let me write this term phi psi n1 is equal to sigma m not equal to n m whatever is there inside that n en0 minus em0 into phi m, or m, just m. Okay. Now I will calculate each of those components corresponds to different m. So first m is equal to n minus 4, and we have to choose the operator which is actually changing this n into n minus 4, which is nothing but a dagger raised to 4, right? That is only term in a dagger that I know, so I just put it that is giving you that term, and this component is going to be, so a dagger acting on n, what it will produce is root n plus 1 it will produce at the first place, then it will produce root n plus 2, root n plus 3, and root n plus 4, and finally it will be producing the state, sorry, this is wrong, this is correct for n plus 4, and finally it will produce the state n plus 4 and n plus 4, and n plus 4 will give you 1. So this is a coefficient corresponds to that particular state.